Hello, welcome. This is the next FP1 video. This is we're getting towards the end of FP1. This is the second video, which is on the series of proof by mathematical induction. And what I'm going to be doing today is it's a second little bit talking about proving that an equation, okay, is divisible by 4. In other words, the answer is divisible by 4. Now, I'm probably not wording that very well, but hopefully, obviously, you'll see what we mean. So, we've got an equation, so a function of m is equal to 3 to the power of 2n, and then obviously you add 11, okay? We need to prove that whatever n is, okay, if all positive integers, it's divisible by 4. Now, the way we start this and the way we answer this is very, very similar to this. Is it serious? No. Is it? No. It's similar to the series, but it's also not quite the same. In other words, the first thing you do is you still prove it is. So you do f of 1. Okay, which is obviously 3 squared, because 3 times the power of 2 times 1 is obviously 3 squared, which is 9 plus 11, which is obviously 20. And you can divide 20 by 4, okay, which obviously gives you 5, a positive integer. And if it's true for 1, you don't need to do it's true for 2, because it's not series, so you can just assume it works, okay? So therefore, you assume true for n equals k. In other words, you sub k where you would see n. And this is kind of, you do it in terms of your left hand side and your right hand side, where your fn is your left hand side and your right hand side is your 3 to the power of 2n equals 11. Okay, so if you assume true for n equals k, f of k is equal therefore to 3 to the 2k plus 11. Okay, and if it's true for n equals k, then you could say, well, therefore we assume it to be true for n equals k plus 1. Okay, so simply just sub in k plus 1 where you would see n. Okay, so f, and still the left hand side. Okay, so f of k plus 1 is equal to 3 to the... Now, it's not 3 to the 2k plus 1, because remember this is 2n, and we're subbing k plus 1 to be n. So it's 2 times k plus 1, in other words, it's 2k plus 2. Alright, so it's 3 to the power of 2k plus 2, and then it's all plus 11. Okay, so the next thing you would do, well, you would naturally go, well, we've worked out what n is, k, okay, and you sub that into part of the equation for n equals k plus 1. Well, you don't, and that's because what we do here is we do to work out the next step. What we have to do is do f of k plus 1 minus f of k. Okay, because that's saying the next stage up is also divisible by 4. Okay, so the difference between them is the step up, so therefore that step up is divisible by 4, and if the step up is divisible by 4, and then we assume it's the same step up each time, so it's all divisible by 4. Hopefully that makes a bit of sense, but as I said, you don't really need to know the background on that. But we've got a problem here. This is 3 to the power of 2k plus 2, and this is 3 to the power of 2k. Now we can't add them together, or take them away, sorry, because they're not the same power. You can't take 3 to the 2k away from 3 to the k, for example. So what we need to do is give them the same power. In other words, you need to do a little bit of working out. So 3 to the 2k plus 2, well, we need to make that have the same power as 3 to the 2k. Well, there's a 2k in there, so what you do is 3 to the 2k is equal to 3 to the power of 2k plus 2 is equal to 3 to the power of 2k times 3 squared. Because obviously when you add times indices together, you add them. It's a simple C1 bit of knowledge, okay? So what we do there is we it's a similar thing of subbing it in, okay? Now, because we know that is equal to 2k plus 2, and 3 to the power of 2k plus 2 is there, we just sub that in to f equals k plus 1. Okay, so f equals k, so the f of k plus 1, okay, now becomes 3 to the 2k times 3 to the 2 plus 11. Okay, and you put that in brackets. Now obviously you can do that 3 squared is 9, so therefore this 3 to the 2 times 3 to the 2k becomes 9 to the 2. 9 times 3 to the 2k, sorry. And you put that in brackets and you add 11. What we said was we need to work out the difference between f equals k and f equals k plus 1. So you do f equals k, f of k plus 1, take away f of k. So in other words, we do 9 times 3 to the 2k plus 11, and we take in all of that away from 3 to the 2k plus 11. Okay, so quite clearly the 11s cancel. Okay, so it's 9 times 3 to the 2k, take 3 to the 2k, which obviously gets us 8 times 3 to the 2k. Now we need to show it's divisible by 4. Well, it's 8 times 3 to the 2k is the step up. So obviously that's divisible by 4. We can take 4 out as a common factor. So we're left with 4 times 2 times 3 to the 2k. So therefore, that is your proof. That it doesn't matter what this 3 times 2 to the k is in terms of what is k, all we know is divisible by 4, okay? And that's proof that this equation is divisible by 4, okay? So the same principle applies as you prove it's true for of 1, okay? Obviously, a particular statement it might not be divided by 4, it might be divided by 6 or times by 2, whatever. And then you do assume for true equals n equals k, and then assume for true n equals k plus 1. Now, there are more complicated questions than this, but what we need to do is we need to give these two the same power, okay? Now, that 11 might have had a power associated with it as well, in which case we'd need to apply the power to that as well. So then what we do is when we've got them in the same power, therefore we can take them away, as we've done here, and then whatever it's asking you to do, so if it's saying this needs to be divisible by 4, obviously it needs a times by 4 in the end, okay? Because obviously, therefore that can be divided by 4. Okay? So, hopefully you can understand where we've got now. Now, I don't want to go into too much detail, because as I said, I'm trying to get through all the topics. But, as I said, the principle applies. The first step you do, it's kind of quite similar to the mathematical induction by series. Okay, so the first thing you do is prove it's true for f equals 1. Now, you don't need to do f equals 2, etc. And then your second step is doing assume true for n equals k and n equals k plus 1. Okay, which is fairly kind of standard. If you have, so I thought I had a proper guide here. Yep. And then the third point is if it doesn't already, which you probably won't do, make the term, so make this here the same power as the one in n equals k plus 1. So make the power involved in n to the k, power in n equals k, have the same power as n equals k plus 1. Okay? And then the fourth step is kind of what we've showed over here. So the fourth step would be doing f of k plus 1 and taking away f of k. Okay, and then your fifth point would be factorising it, so to get it into this state. Okay, and then there's something actually I didn't do. Well, I kind of explained it but didn't say it. You need to write a sentence, and that's just any old sentence. That's a sentence that says, well, because whatever this is, okay, in this case it's 2 times 3 to the power of 2k, okay, therefore, because it's times by 4, it's therefore divisible by 4, which is what we can state here. Now, I'll just get you the proper definition, so I'm just not missing anything else. Do apologise. FP1. Well, actually no, I won't do that. You can have obviously a look at various questions online, and it will give you obviously what the examiner is looking for in terms of the actual sentence. But it's just a case of highlighting the fact that it's therefore divisible by 4, or whatever it is that you might be being asked to prove. Okay, so thanks for watching. Hopefully it's been helpful, and we'll see you in the next FP1 video, which should be the last one, and that is all about proving by mathematical induction. What's the next little bit? It's to do with matrices. Okay, so I just forgot what it was called. Stupid. Okay, so thanks for watching. Hopefully it's been helpful, and any comments or anything about what I've gone through, or if you want me to do some more questions on this, please do let me know, and I'll put some more up. But I'm kind of hoping that's kind of similar to the one we did previously, just with an extra little twist, which I highlighted through that question. But they will all be the same, just different, varying difficulties of that. Okay, so we'll see you in the next video. Thanks for watching.